इसके बटन आएगा ना.
This one, the one just before 1.3.
Okay, this one.
Yeah,
Okay, so
for
what
the
this means
assumption.
is, okay, okay, so let me just explain this. Okay, so generally, the strongest assumption is that the samples are independent and identically distributed. You understood that part?
Yeah, that I understood.
So that is the strongest assumption. If we can make that assumption, then we can say for sure that if you have a large enough data set, then mu hat will tend to mu. So that is when you make the assumption that okay, the samples are IID. That is why I can say that mu hat will tend to mu when the number of samples is large. However, in some cases you cannot always make that assumption depending on the data.
Okay.
Yeah. So depending on the data, you cannot always make that assumption. So what happens is, in some cases, you make the assumption that okay, I cannot say that they are IID for sure, but if I can say that they are uncorrelated, like sample x1 comma y1 is not related to does not have a correlation form with sample x2 comma y2 or with sample x3 comma y3. If you can say this with some certainty, even then you can make you can still say that mu hat will tend to mu. So you have reduced the strength of the assumption you're making. Other you have reduced, instead of using a strong condition, you're now using a weaker condition.
Okay.
Because see, independence and correlation, if you see now, if something is independent, if two random variables x and y are independent, then they're definitely uncorrelated. But if two samples x and two random variables x and y are uncorrelated, that does not necessarily mean that they are independent. So that is why independence implies that it is uncorrelated, but uncorrelated does not necessarily imply that the random variables or the samples are independent. So what you're saying is, okay, I'm reducing the strength of the assumption I need to make. So even earlier, if there were some data sets where I could not say for sure that okay, these samples are IID, now if I can say for sure that the samples are uncorrelated, then I can still um, make the assumption that mu hat will tend to mu. I can still say that for sure.
But like, how do you decide that? I mean,
Okay, how do you decide that a sample, a data set is independent or uncorrelated? Is that what you're asking?
no, like how do you decide? So I understood when it's independent, then you can say that that is equal to the sample mean. But how do you say that for uncorrelated as well? Like how do you come to that conclusion?
Okay, so if they are uncorrelated, that means suppose there is some data generating process that you are using, right? Right? And if you are drawing samples on that process, and your first sample is x1 comma y1, and your second sample is x2 comma y2, or then you have x3 comma y3 or so on. And if these samples are not correlated to each other, that means they are sort of like independent draws, right?
Yeah.
So that is why we are saying that even if I cannot say with certainty that these samples are all independent, if I can just say that they are uncorrelated. Okay, so
Then yeah.
yeah, I understand your question that I know I haven't explained it sufficiently, but I can't think of an example where I could say for sure, okay, this is uncorrelated but not independent.
Right.
Maybe I'll find some example if I have of that, and I'll let you know next time.
Yeah, definitely.
Okay, wait.
Thank you.
I have one. So you are looking for example where the samples are uncorrelated but they are dependent. So wait, I just path give screen control.
एक second. I'll stop sharing.
Just to drill the concept home, let's say you have a random variable x that's sampled from a standard normal distribution. Then you have another random variable y, which is just x square. So now here x and y are obviously not independent because they are like, as you can see, once you know x, you can get y. but correlation between x and y would just give you expectation of xy minus expectation of x, expectation of y is x square, so this will give you expectation of x cube minus expectation of x times expectation of x square. So first we know expectation of x is 0 because it's standard normal, so this term is 0. And for standard normal, there is a thing that all the odd moments of standard normal are always equal to 0. So because it's, if you see that it's like a kind of a even, it's symmetric around 0. So if you take any odd normal, then it's like it's odd function. If you remember from your 11th, 12th class, so like x, if it's around x cube, so even this comes out to be 0. So the correlation between x and y is 0, but they are dependent here. You can see for the proof for yourself. The odd moments of a standard normal are always.
I get it. Thank you.
Yeah. Stop. Yeah, you can go ahead.
Yeah, is my screen visible?
Yeah.
Yeah, it's visible.
Okay, so does anyone else have any other questions on the part that we have already covered, or should we continue with the part where we left off last time?
I think
Okay.
we can continue.
Yeah. Okay. Okay, so we covered the bias variance trade-off. We covered the two decompositions, and then after that, okay, yeah, yeah. Now, what it means is, okay, right now the view that we have of ordinary least squares is we have some data samples, which is x1 comma y1, x2 comma y2, and so on. And from that we find the parameters, we estimate the parameters that will best give the relationship between x and y. Now, there is a different view as well. Rather than saying that, okay, this is okay, by using ordinary least squares, regression is smooth. There's a different view as well of how you can generate an estimate for parameters that will give you, rather than just using the normal method that we use. There's another view as well. X by, we say it's a line b0 plus b1x, and we ask for the best values beta naught beta 1 of b0 comma b1, which is what we normally do. We say a plus x and try to find the parameters a and b. Now, when we use the mean square because we want to minimize that. By minimizing it again from 1.30 to 1.29 to 1.30, we again use the law of total expectation. After that, again we use the definition of variance to simplify it. Then okay, 1.32, we can see that the first term does not depend on beta naught or beta 1, so it doesn't make b0 or b1. So we don't need to, even if we derive it, the derivative of that part will be 0 with respect to b0 or b1. The derivative of the second part, if we calculate with respect to b0, we get these equations. If you calculate the derivative with beta b0 and b1, you get the values beta naught and beta 1, which will give you the smallest value of mean square. And I think this is a formula which you must have covered in machine learning as well, I think, in the class that we have in college. Yes. So finally what we get is, we get beta 0 is this.
Can you also like point out the formula, because we didn't really have proper machine learning class last semester before COVID, so.
Okay. So see, you understood till this point how we came to 1.32?
Yeah. Like I understood the law of total expectation and uske baad. And then we yeah.
Yes. And okay. Then after that, once we reach this point, once we reach 1.32, now whenever you want to minimize the function, what we do is we normally take a derivative of it, right? We take the first derivative of it and we equate it to 0. Now here our parameters are beta 0 and b0 and b1, and we want to minimize the mean square error with respect to b0 and with respect to b1. So we have to calculate two different derivatives. So the first partial derivative is with respect to b0, And since the first term doesn't contain any b0 or b1, you can just eliminate it. It's gonna always want to be 0 with this when you calculate the derivative. So in the second term, you calculate the derivative with respect to b0, you end up with this equation: beta 0 is equal to absolute expected value of y minus beta 1 expected value of x. Similarly, if you calculate the derivative for b1 uh, with respect to b1, you get this equation: b1 beta 1 is equal to covariance matrix of x comma y divided by variance of x. I think Fenil explained the matrices yesterday, how they would look. That covariance of x comma y and
Yeah.
yes, and yeah, okay. So then we assume that mu x is of the shape b0 plus b1x, mu of x. And so if we substitute the values of beta 0 and beta 1, this is the final equation that we end up getting. Now, okay, is everyone clear till this point how we came to this equation? And this is the optimal mean square error. This is the optimal line that we can get. Yeah. This is the optimal line that we can get when we have these data points. If we are assuming the shape b0 plus b1x, if you assume some other shape, if you assume a quadratic shape, you might get some different answer if it fits the data better. But for the line that we have assumed that it is a plus bx, then for that, this is the optimal answer. Okay. Now what we need to find is we need to find these different values. We need to find the expected value of y. We need to find variance of x comma y. We need to find variance of x. So there are two approaches to do this. One is uh, you have the data set, calculate these things from the data set and substitute it over here. So basically you are using the sample values of covariance and variance, and you are using it as the true values, which is what you need here. So what you're saying is, one second. What you're saying is covariance of x comma y. This is hat because this is what you're getting from the data set is tends to covariance of x comma y. Similarly for variance, you can say the same thing. That's the assumption that we are making, that our data set is large enough to actually obtain a value for covariance and variance which is close to the true value. So we can directly get the answer accordingly. You can directly get the line. Or the second way would be you have the mean square error. This is the mean square error. The method that we use to try and minimize, right? We use we have this loss function and we try to minimize it by using the in sample. Yeah, we try to minimize it by using some operator, and we finally come to hello, am I audible?
Yeah, you are audible.
Yeah, because difficult. Okay. Yeah, so what you see finally the answers which you get beta 1 and beta 0, the estimates, they all lead to the same answer, because see, beta 1 is still by n summation of yi minus y, what do you call it, y bar x into x minus x bar divided by v hat of x, which is the same as the value for beta 1 which we got. The numerator is still the covariance and the denominator is still the variance. So both these approaches actually end up to the same answer. Okay, so now you know that mu hat of x is beta 0 plus beta 1 of x. Okay, is everyone clear to this point? Did you guys understand this, or do you have some questions about this? What we did here? Jay, Ananya, Josh, anyone?
I think it's
Okay.
clear like till that.
Yeah, okay. Yeah, cool. Okay. So now we have found the values which are using our data points. We have found what is we can use data point You can either calculate the covariance and variance of the data points itself, or what you can get using the gradient descent. You'll find what happened directly. This one over here, beta 1 would have been covariance of x comma y upon of x, and over here also beta 1 means the same thing. This means the same thing. Okay. Now we know that okay, our estimated estimator, approximate estimator, which is mu hat of x, is equal to beta naught hat plus beta 1 hat of x, beta 1 hat x. Now you substitute the values of beta 0 and beta 1, which you have gotten from the equation above. And I think this derivation is pretty straightforward. The only thing is this part. This turns out to be the variance of which is what we have here. That is the only part which you take out, and okay, this is straightforward. There's nothing over here. So finally, what you can see is you can represent mu hat of x as this term, which is basically a weighted sum of different yi's. And how do you weight it? How do you calculate a weight given to each yi? Use the corresponding xi for so each data point. So let me draw this. Yeah. Okay. So suppose your date. This is your data sample. This is your something like this is your data set. Okay. I want to the I want to predict the value of y at this point. I want to predict the value of y at this particular value of x. So what I'll do is, according to the difference of x from all these different data points.
But
Yeah.
your voice is cracking a bit, like in between.
Okay. Am I audible? Am I clear? Actually, my internet is a little unstable at times, so that happens. Am I clear now?
Yeah, you're clear now, but sometimes in
Yeah,
between it
sometimes.
get cracks.
Oh,
It's
okay.
clear now.
Just
You can continue.
yeah, let me know. Uh, I'll repeat whatever. I'll repeat this part again. Okay. So this is just the data set that we have. These are different points xi comma yi, and now I want to calculate my what would be my estimate for yi at a particular point x. So this is that blue line is my value of x, and I want to calculate what would be my y at this point. So what I'll do is I'll basically according to this equation, what I'm doing according to its distance from this point. So depending on how the distance from, I guess I cracked again, right? I think my voice must have gone again because there was a notification that my internet is unstable.
Yeah, it was a bit.
But did you guys get everything, or was it
No,
completely
like
gone?
you can continue.
Okay, yeah, I'm sorry about this. I can't really do anything about it. Okay, so for different depending on your points, you would calculate these distances, and accordingly, you a particular weight that you would assign to the y according to x for particular. So what you do is you have to calculate two things: part of your data sample and you have to use xi, the weighted average. Yeah, a prediction is a weighted average of a regression where the weights are proportional to how far xi and x both are center assume y is the center, calculate the distance of each data and summation of all those weights with their corresponding. Okay, this is what we're doing. However, you guys can see that the problem over here is we are we are assigning the weight of the center of the
Parth, can you repeat the last part? Like
Wait, just
your
forget.
voice completely got cut off after that.
Yeah, just forget this part.
Means,
Just this 1 second.
yeah.
I made a mistake over here. I'll repeat this part. Okay, this is my x and this is my y. Okay, my points are arranged such that right now I'm making the assumption that my points are arranged such that the mean x bar is 0. That means the mean is at the origin. X mean, the mean of the x-axis, xi is 0. Did you understand that? Hello.
Yep, yep. It's much better.
Yeah. So now, according to this equation, what I'm doing is, if I want to calculate the value of what my corresponding value of y would be at this point, whatever this point is, what I'll do is I'll do two things. First thing I'll do is I'll calculate the distance of this point x from x bar. This is x bar. I'll calculate the distance from x from x bar. I'll also calculate the distance of each point, each data sample. So calculate how far each data sample is from x bar. Accordingly, I'll assign a weight and I'll multiply with corresponding values of y, and the weighted sum will give you the for what should be corresponding value of y at this point. Okay. Now the problem over here is we are assigning weights according to the distance of these points from the mean, not according to the distance of these points from the point that we are considering. Ideally, what you should say is, if this point, if this is the point I want to find the weight at, then this point should be considered the most because it's closest. There should be less weight assigned to the second point as compared to the first point, because the first point is obviously closer. So I would say that it is more representative of the trend at the particular point that I want to calculate at this point. Is that understood?
Yeah.
Yeah.
So this is the problem with linear regression, that it gives weightage to different points according to how far they are from the mean, not according to how far from the point that we actually want to calculate it. So that seeing it seems that there could be a better method rather than using this. So what you do is this brings us to what smooth. So did I cut out again?
I think in the last sentence, immediately after the when you cleared that mean part, I think after that you got cut off. About a minute.
Okay. Yeah. Okay. Yeah. So sorry. Yeah. Okay. Okay. So both of these, basically, what we are doing is we are doing linear smoothers, and both the sampling and least square regression are both special cases of linear smoothers, which use this representative formula where mu hat of x is the summation of a weighted average of the different yi's, where So what you can see is they are known as linear smoothers because the predictions are linear and the response is yi. So you're basically only summing up the yi's. You don't carry out any non-linear operation on the yi's. However, these can be non-linear in the weighting function. So the relationship between the x's, x and xi, can and usually is non-linear. Okay. Yeah. Yeah. So what are the different types of linear smoothers that we have? The first one is you could use k nearest neighbor regression. So the first thing you could do is you could do nearest near regression. So in that case, what you would say is, if these are my points, and I want to calculate the value of y at some particular point. Okay, I want to calculate the value of y at this point. Then the closest point is, then I'll only consider the closest point, which is this one. And what I will do is I'll assign a weight of 1 to it, or else for all the other points I'll assign a weight of 0. So basically the y at this point will be equal to the y at this point, at point 2. Okay. However, as you can clearly see that this leads to this makes it too sensitive, because even though any outlier any single point will make a difference in your prediction, which should not be the case, because any outlier will can easily reduce the performance of easily reduce the accuracy of your answer, which is not what you want to do. So instead of using only one neighbor, what we do is we use k nearest neighbors. We assign a value of 1 by k to the k nearest neighbors of x. So 1 second, I'll draw on the line. Yeah. Okay. So these are different data samples. What I'll do is, if I want to calculate at this x, if this is my x where I want to calculate my mu hat of x, I'll take k nearest. I'll take 1, 2, 3, 4, and 5. Suppose k is equal to 5. I'll take these 5 points. I'll assign a weight of 1 by k to each of them. The yi is for each of them, and I'll sum it up, which will give me a good estimate for what should be the value of y at this particular value of x. Okay, yeah. So what happens? Why is k nearest neighbor better than nearest neighbor? When you only have one point which you are considering, if there is a lot of noise in that single point, then there will be a lot of noise in your answer, in your estimate. However, if you are estimating over 5 or 6 points or even 10 points, what happens is the noise averages out. So you have a better answer rather than just having one outlier. Depending on just one outlier point, you depend on an average of 5 points, which is better. So that is k nearest neighbors. However, depending on the value of k that we use, it will vary. So it will depend. It will vary how smooth or noisy it is. So if you use a value of k is equal to 1, which is the same as nearest neighbor, it will be very noisy. However, if you use a value of k is equal to 5 or k is equal to 10, then it will be more smooth, which is what smoothing is. So here k represents your parameter which decides how smooth your final function is. If you use a larger value of k, your function will be more smoother. If you use a smaller value of k, your function will be, yeah, see, in this case, this graph explains that. If you are using k is equal to 1, the red graph,
But
which is very spiky. Yeah.
okay,
Yeah,
so
what are you
part
saying,
like
Guru?
I had a doubt. Okay, मतलब, like yeah, so like you said, कि, like like based on the value of like the k, this function will be more smoother. Like so, like that's more smoother function would lead to like overfitting too. No, like
No,
is
if
there
you
any like limit or like how do you control like
no,
that
it's actually the
smoothing
other
to
way
like?
around. See, right, it's the other way around. And look at this graph. When you use k is equal to 1, your graph will try to fit to all points in the data set, the red line. Okay, I'll draw a graph in the side as well.
Yeah, okay, okay. It's trying to remove the noise, so it will like find out the estimate.
Yeah. So suppose this is your graph. Okay, and if you are using uh, yeah, if you are using k nearest neighbors, if you are using k is equal to 1, what will happen is it will try to fit to all points individually, which is not a smooth graph. Now if I was using k is equal to 2, what would happen is it would be able to average out. So suppose I was calculating a point that I was calculating at this point, I would be able to take the average of both these points rather than just moving towards one of them, which would make it a smoother curve. Did you understand that? So
Yeah,
maybe
yeah.
I could, rather than going through this, I would be able to come with a smoother curve rather than just such a spiky curve. So you can see that in this graph where k is equal to 1, the curve is very spiky. Where when you start increasing the value of k, the curve starts becoming smoother. So the blue line is the smoothest.
But like in this case also there would be a limit, no? Like because if more smoothing would lead to like underfitting, so
Yeah.
like not getting much of data, like kind of
Okay.
way.
So the extreme cases if k is equal to n, where if your data size is n, the data set is n samples, and if you make k is equal to n, then you get the global mean, because for each data point what you'll do is you'll calculate the average of the whole data set. So you
Mm-hmm.
would just get a straight line like this, which would be the
Okay.
mean, which is
Mm-hmm.
what they've shown here. Yeah, this
Okay.
dot dot dot.
Okay.
So this is what is known as kernel smoothing. Wait, did I miss something over here? Yeah, this is what is known as kernel smoothing or kernel regression. There are different names for it, Nadal and Watson regression. So what you need to do is you need to use a kernel function which allows you to assign a weight. So there are some properties for these kernel functions which are mentioned over here. K of xi comma x is greater than equal to 0, because obviously you can't have negative distance. K of xi comma minus x on the individual arguments. So instead of writing k of xi comma x, you can also write it as k of xi. Minus x. Instead it was question means x if the point from your uh, hello, was I kicked from the meeting or something?
Sorry, can
Hello,
you repeat?
did I leave the meeting or something?
No, I think you have screen sharing got stopped. You are there in the
Sorry.
meeting.
Yeah. Is it clear now?
Yeah.
Hello, can you hear the screen now? Yeah. Yeah.
Yeah,
Sorry
yeah.
for that.
We
Yeah.
can see the screen.
So there are two types. They've given two examples of the function. One is the density of the uniform function, uniform kernel, which is also known as the boxcar kernel. And the second is the density of the Gaussian curve, which has the standard Gaussian normal curve, which with the square root of h as your standard distribution. So here in the when we are doing k nearest negation, according to the value of k, the smoothing would increase. If you increase the value of k, the smoothing would increase. So that is also known as a bandwidth parameter. In most of these functions, h is your bandwidth parameter, which is how you decide how much smoothing you want to do. So okay, so let's see the boxcar kernel. What the boxcar kernel does is, for any point, it will calculate, it will create a square next to it, around it, of size h by h. And whichever points lie in that square, it will take an average of those points. That's what the boxcar kernel does. And the Gaussian kernel, it you guys, I think Daniel explained the equation for that, right? Yesterday. 1 by square sigma square root of 2 pi e raised to minus half x minus mu by sigma the whole square. Yeah. So here sigma is equal to square root of h, which is what you are using here. When mu is equal to 0. So that is how you use the Gaussian distribution. And according to the x will be replaced by xi minus x, where x is the point which you actually want to find the estimate at. So according to how far each of these points is from your value of x, you will assign a weight to it. So that's what they explain over here. So k of xi minus x is xi comma x is large if xi is close to x. So it will place a lot of weight on the training points which are close to it. And if your points are far apart, it will give less weight to it. That's it. Yeah. Okay, yeah, these things, this explains the same things. And that the box kernel simply takes a region of width h on the point x and averages the data points it finds there. The Gaussian will do something like, the curve. It, according to this curve, it will assign weight. And so the points which are closer will have larger weight. Whereas the box curve, what it does is it assigns weights according to this square. It assigns equal weights to all the points inside the box, whereas the Gaussian will use this curve to decide how much weight to assign. So the bandwidth h controls the degree of smoothing. As h tends to infinity, you are basically taking the global mean. As h tends to 0, of nearest neighbor, we use k is equal to 1. We tend to get spikier function. So depending on our situation, we need to know what h to use. So I think we cover that in the later chapter, how much h to use. We cover that in the third chapter, model evaluation. Okay, so 1.5.3 onwards, this is basically just, okay, did you guys use 1.5.3?
I haven't read through. I haven't read through 1.5.
Okay, so 1.5 is not that important. Basically, just whatever we have done till now, it just it shows you how to calculate the variance. It shows you how to calculate the estimate using the smoothing theory rather than using linear regression. So okay, I'll do one example of this weight because I
Or
didn't
if you
read it.
want,
Yeah.
we can read it and maybe come back with doubts if we have next time.
Yeah, I think that would be, I mean, works better because I'll just explain this one because this is the one which is slightly confusing. Apart from that, I think most of them are pretty simple. Okay, so this is the formula we saw from the formula that mu hat of x is equal to this thing, right? If you want to calculate the v mu hat of x, this is the formula. So this formula that variance of a plus b is equal to variance of a plus variance of b plus covariance of a comma b. This is just an equation for variance of a plus b. And so according to this formula, what we are saying is that the points are uncorrelated, right? That the noise is uncorrelated. That is when we say that covariance of a comma b will be 0. which is why you can just bring this variance inside the summation. Since w of xj comma x is just a constant, it won't vary, it's not a random variable, so you can just bring by using this, I think, very known a x variance of x. And yeah, and so what now in the last point we are making the assumption that this is a constant sigma square, which is what we're doing. Yeah, that's it. The degrees of freedom and that part, if you want to solve the question, then you'll have to read through this, but it's pretty straightforward. There's nothing tricky in this. So if you guys have any doubts, you can let us know next time if that works for you.
Yes. I don't mind.
Yeah.
So I think Fenner will start the second chapter. Okay, so while Fenner is getting set up, can I ask you guys if you actually understood everything? Like, I just want some honest feedback because this is the first time I'm explaining this to someone. So did you guys get it or was it unclear?
Like most of the stuff was clear. I think for me, I can speak for myself that when I read through it again, then I'll be like pakka sure of it. But like yesterday's lecture, during the end, it's very clear. But I had to read it again then.
Okay. So if you guys have any questions, you can let us know in the next, or you can even just ask on the channel. We'll be able to answer.
Yeah, same as Ananya. Like it was clear, basically, but we'll need to go through the text once, so like that way. So if there are any some other doubts, then we'll post on channel.
Okay.
Yeah, hello. Am I audible?
Yeah, you're audible.
Yeah, you are audible.
Yeah, so did you go through the second chapter? Once at least. Or no? Nice.
Yeah, like I had gone through it super similar, like not in depth.
Yeah, okay. So,
Kind of broad overview.
yeah, so if you go through it now or even later, so there is this entire book on that. This is just one chapter that summarizes everything, but by same author Shalisi, the book itself is the truth about linear regression. So there is quite of theory in it, and if you face some doubts, you can also refer to this. But yeah, this assumes that you have read this. But yeah, it's okay. So as Parth said, there are variety of functions. So generally, how do you annotate on screen?
Sorry, I had one doubt from the previous chapter, like,
Yeah.
so regarding like deciding which smoother to use, like, so is there any some convention or like how we decide kind of which smoother will be better, like in which scenario, like, well, there might be cases where like let's say two smoothers are like let's say better for a particular like kind of problem like regression problems.
Yeah, so smoothers are general. So yeah, in your Shalisi talks a lot about when to use linear regression, when not to use linear regression and stuff. But apart from that, like these, as Parth said, the Nadara and Watson regression, that the smoother depends on the choice of your kernels. So there are many. The Gaussian kernel is the most used one because it's quite general, but those are kind of general smoothers. But yeah, it's like model selection. You will never know like which one is the best unless you try with all different kernels and
But
different models.
Okay, but is it like we are using Gaussian highly because like we try to like kind of like normalize data and like keep it basically close like with a mean of zero and like that way. So we try to like model it with Gaussian only like that way. So is it that the reason like we use majority of time Gaussian kernels only like in most of our problems?
Yeah, so
At least for
Gaussian.
what I have encountered.
Yeah, so you use Gaussian kernel first of all because it works, and like as there is a thing as called central limit theorem, where Swapnil was talking about it earlier, that when you have enough data, then no matter which distribution they come from, but the mean of that data is always Gaussian distributed. It's kind of like central to normal distribution, and there is also a theorem that you can represent any continuous smooth function with the Gaussian with n number of Gaussian kernels. So it's kind of ubiquitous in that sense, and it's like what you need in linear smoothness. The important thing is that it should assign more weight to the points that are closer and less weight to the points that are far, and that's kind of one of the important properties of Gaussian kernel as well.
Okay.
Regarding what Jay asked regarding the choice of the best smoother, you kind of wanted the answer to what is the best smoother in terms of linear regression. So I think that would depend a lot on data distribution also, right?
Yes,
So how your data is basically that so you need to try multiple options and then decide, because different things have different distribution in terms of data points.
like as in this there was this diagram, it can be clearly seen that instead of even k means uh, two-dimensional parabola, 2-degree parabola would have been a better fit than a linear regression or 3-degree curve or something like that. So it depends highly on data, and that's what we'll talk about in in the linear regression, when to use it and why to use it, and what cautions you need to precautions you need to take before using it. So first, just connecting to previous chapter, um, Parth, how do you annotate on screen? Do you know on Zoom?
What? No. Maybe wait.
एज Penny edge है तो edge को edge पे होएगा. You have edge.
Yeah. But
When
no,
you share your screen, you get an option. When you share, like when you're trying to share a screen, you get like an option to annotate.
No, I think you
I
must
know,
have switched that off.
but I cannot see it. So, do you
I
know where
mean,
that
you
option
must be.
is?
Like right when you're sharing the screen, that when you're like choosing which window to select, that time I think aata hai. Like there's a sign also.
Wait.
Well, you must have switched off that setting. You'll have to start it again if you want that setting. You have to start the meeting again.
Okay. Okay, never mind. I'll do it on Edge. Wait a minute. I'll open it in Edge. Oh wait, I might not have Edge in this computer. Anyways, yeah. So let's start. So if you recollect that y is always equal, you assume that y is equals to nu of x plus epsilon, where epsilon is the noise. So here we are fixating nu of x to be a linear function, that it's just linearly related to x. Yeah, that's it. So if the optimal choice of nu of x is beta 0 plus beta 1 of x. Yes, it would be better if I could just annotate. Yeah. Sorry about that. So as I was saying, you can see this curve is something that was generated from something like this curve, and the different points are just like the epsilon, the noises that you see in your data. So if it's something like that, then you know which curve fits the best. But now you are assuming that whatever the data is, you will always fit a linear line. So your data might not be linearly distributed, but you can always, thing is you can always put a linear fit to your data. So even if the data is generated from this curve, something like points are like that, but still you will get a linear fit, something like this. So here y is equals to mu of x plus epsilon, and mu of x is equals to uh, is equals to beta 0 plus beta 1x. Now, all the deviations that might fit here are captured in epsilon. So whatever you are ignoring because of your linear fit are in epsilon. So naturally, if it's a linear fit, then epsilon will just be some random standard noise. But if it's not, then epsilon will also account for all the biases that you have missed. So like example would be if this is the actual curve and this is your linear fit. So as you can see, as x increases, the epsilon is basically the difference between the y value and the predicted value. So you can see that as x increases, the epsilon changes. So it's like if it's a linear fit, if the data is actually linearly distributed, then in majority of the cases, epsilon would be independent of x. But if it's not, then you are missing out on something, and that is captured within the epsilon noise. So you can't just assume that epsilon is always independent of x. So that's what we'll start with. So as we had seen previously, any optimal predictor would be in the form of conditional expectation of y given x. So, but now we are, as he's saying, the decision is on our part that this function is equals to beta 0 plus beta x. This decision can be good, can be tolerable, and can be very wrong. So, but why? Why does it make sense sometimes to make such a decision that x is linearly distributed? Because if you remember that it tells about Taylor expansion, that if you are just interested in points near x is something that you want to predict, then you can, if you Taylor expand the function, then you can just imagine that all of these doesn't contribute much because x is far away from you, and this is what you are left with. So this is actually a linear function. So it's like the first order Taylor expansion will give you a linear function, second order will give you a quadratic function. But if x minus nu is far away, then x minus nu square and all those terms will just go to 0. And then this is what you are left with. So sometimes when you want to predict around a point u, it makes sense to have a to know what kind of result linear regression gives to you. So yeah. So now we said y is so as we know, beta is your mean square error would be y minus mu of x the whole square. Y minus mu of x the whole square, and mu of x is our assumption that it's beta 0 plus x beta. So this naturally follows. And now if you optimize it just like as Parth had did before, the only difference is what Parth did in first chapter was for univariate case, where if you just differentiate LHS and RHS and equate it to 0, then you would get this equation equal to here. Yeah, so this is what your beta comes out to be. But if you try to directly expand this, then I guess you would have to know about vector multivariate calculus, and if you know, then you can follow the same derivation as before. Just you will have to, instead of difference. Do you know differential calculus? Should I skip it? I guess yeah, I should skip it because it would be too much of a diversion. So yeah, if you want to know that, you just see about differential calculus, and then you will the proof is similar to just above, and that's what you end up with. And it's similar to what you saw. Instead of just in previous proof it was sigma square here, but now instead of sigma square we have the inverse of variance matrix, and this V is yesterday what I taught you, the covariance matrix of X with itself. So now we everywhere X is a vector. Just let me know if you are not familiar with these. So if it was not clear, that I think this was also covered in Andrew and G's course as well. So beta 0 plus X would be this is X1 data point, this is X2 data point, and so on. This will be your beta features, beta 1, beta 2, beta 3. So if you equate that, you will get your y. So it expands kind of to y is equals to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 and so on. So that's just writing it in matrix format. So what you get is actually this. Beta is equals to V inverse covariance of xy, and V inverse is the covariance of x itself. So what one can also say is why we are not just doing linear regression in multiple dimensions, just like we do it in 1D case. Like first forget about whatever we know about x2. First just solve for x1 dimension, then just solve for x2 dimension, and then just aggregate the values. So why can't we do that? Because in what I was explaining in normal distribution, you can't do that because the dimensions itself are correlated. X1 is correlated with x2, so you can't just remove those correlation. But if you do it individually, that's what you are implying, that all the individual dimensions are uncorrelated with each other. This is similar to yesterday's talk on normal distribution. So if the input variables are uncorrelated, V is diagonal. Yeah, so as I told you earlier, V is this is variance in x1 ... and diagonal or are variance, and if these all are covariances. But if all dimensions are uncorrelated with each other, this all comes down to 0. This entire thing is 0, and what you are just left is with all the variances in the diagonal. So anywhere, if all the dimensions of a vector are uncorrelated, then you get a diagonal covariance matrix. Just all the diagonals are variances, and all the covariances of diagonal elements are 0. So what V inverse is doing is it's doing the same. V inverse is kind of decorrelating R axis. So when you multiply it by V inverse, it says that if you can kind of split V inverse into V half. I don't know how familiar you are with linear algebra. Did you all read this? Do you have any doubts, or should I go into depth and explain? Any pointers? Thanks. Hello, am I audible? Hello.
Yeah, you're audible. Jay, Ananya, Josh, did you understand it, or did you have some questions? At least let us know that.
Yeah. This is the fourth point what he's speaking about, and it's kind of trivial. You can let it go, but if you are interested, then I can explain. It's not trivial, but it's not necessary for because of lack of response. I'll just skip it. Let me know if you have any doubts.
Can you repeat kind of like I got just disconnected from the video. Last one.
Okay, so what I was saying was the this V is yesterday what I explained, the covariance matrix here in this beta, and what exactly if all of your input dimensions are uncorrelated to each other, then we will always be a diagonal matrix, because at the diagonals we have variances and at off diagonals we have covariances. So variance of x1, this is covariance of x1, x2, and so on. So this is how here you will have always the variances, and here you will have always the covariances. It's also, as I said earlier, it's also symmetric. But if all the covariances are zero, that is all the dimensions are not correlated to each other, then this will all turn out to be zero. So just to drive it how it will look in the normal case, I'll draw a contour plot here. If x1 and x2 are the two dimensions, you can assume this is a contour plot of a normal. Here x1 and x2 are not correlated, but if this is how your normal is, then they are correlated. So if the dimensions are correlated to each other, then you won't have if they are uncorrelated to each other, the B is diagonal matrix. That's what I wanted to tell. And now, but because they are not correlated, you cannot individually do linear regression for each dimension. So that's what he was trying to say here. You will have to do means it doesn't work if you just first do the linear regression for x1, then you do linear regression for x2, because there are covariances within x1 and x2 that you can't neglect here. So that's what he's trying to say here. And how does V inverse? What V inverse is actually doing is V correlating all the dimensions, and how it does that you can read for this bottom line and whatever the fourth point is. But even if you don't understand, it's fine, I guess. So yeah, the equation of beta is this, and here is where the x, the like as Parth was saying, how x's are related to each other, the difference of x with the mean vector, and all of that is encoded within here in the inverse covariance of x y. So how do x relate to each other? So beta depends on marginal distribution of x. Based on what x is, the beta will change to the covariance matrix V if that shifts the optimal coefficient. Yeah. So as was this, if you this was in matrix format, x dot beta. If you just expand it, what you get is your predictor is beta 1 x1 plus beta 2 x2 plus beta 3 and so on. Now, what happens if the V inverse doesn't exist? If you remember, V inverse won't exist when the determinant of V itself is 0. So when will that happen? When will be the determinant of V be 0? So this is what's up name?
Singular
matrix. Yeah, singular matrix. Determinant of V 0, that is V singular. So it indicates that V inverse won't exist. So how does it contrast to in the case of linear regression? So this is similar to solving linear equations that you did in first or second year, that linear equations may have a solution, may have infinite solutions and so on. So if the V inverse doesn't exist, it indicates that one of the column or one of the rows is a linear combination of other two rows. This is an example when a determinant won't exist, because this row can simply be produced by 2 times x. So whenever there is a row or column that is linear combination of other rows, the determinant is always 0. And that is called rank efficient matrix. You can look about in linear algebra. So yeah, what it indicates is that this equation will then have infinite solutions. If x1 is say 2 means in your feature vector, this was also what Andrew and G covered, I guess, in this machine learning course. If you have a feature for length and you have a feature for breadth, and then you also have a feature for parameter. So the parameter, like for pricing of houses or something like that. So parameter is just a linear combination of length and breadth. So it's kind of a redundant feature. And in cases like this, the V inverse won't exist because whatever the values you note, let's say the length is, let's say this is a length column, this is a breadth column, then the parameter would be sum of these two times 2. Basically a linear combination of first two columns. So here V inverse won't exist. So whenever you have redundancy in your features, wherever the features can be reproduced linearly by other features, the V inverse won't exist. And when V inverse won't exist, there will be multiple solutions. So that's what he's trying to say, that if you write the equation in this form, it's the same. If you write the equation in this format, it's the same. And again, if you write the equation in this format, it's the same. So there is not a single optimum value of beta 1, beta 2, beta 3 that will give you optimal. There are infinite values that will give you the same value of your predictor. So that's why what you need to do, there is 3 ways of dealing with this. One of them is you analyze them manually about how they are relating to each other and just remove the redundant feature. One of them is to just get more data, and make sure that there is no linearity between the different features. And the third one is kind of an advanced, and I didn't understand what splines are, but I guess he's covering it in future chapters. So and the prediction and insider now. Okay. So, now what he's telling now, just remember this, here everything that we have discussed right now, we are never assuming that a linear fit would be the best idea. As I shown it in this example here, there could be a curve that is exponential, but yet you would have some linear fit. So you are not assuming that linear fit would be the best idea, and epsilon still can be dependent upon x. So just keep that in mind. Yep. And so now what we are just calculating is this y minus x beta is simply the noise epsilon. And how does epsilon, this epsilon is also called residuals. How does this residual correlate with x? So if you just expand this, what you get is covariance of like this is also kind of linearity in covariance. You can just first see the covariance of y with x and see the covariance of x beta with x. But since this is beta, since beta is constant, you can just take it out. Covariance of x with x is b, as I showed you. So this is v and this is beta. Then v inverse gives you I, and then covariance of ix minus covariance of ix will be 0. So even if you didn't assume that y is a linear fit, yet the covariance of residuals with x itself is always 0, no matter what. So that's kind of what it's kind of a chicken and egg like of thing, that as I said, covariance says you whether it just says you whether the data is linearly dependent or independent. So whatever the beta is, it will be to an optimal value that will ensure that at least the covariance between y minus x beta, the residuals and x will always be 0. But again, this is, but once say you know x, whatever x is, it cannot be said the same here, because generally, as I said, y is equals to x beta plus epsilon, y minus x beta is equals to x. So given x, expectation of y minus x beta given x would be expectation of epsilon given x. But as I said, the epsilon is not always dependent on x. It will be only in the cases where y is truly linearly distributed. So if you have something this. So a linear fit, and all the epsilons will have an, if you sum it, then they'll have an expected value of x. But this is only possible because these dots are linearly distributed, but it won't always be the case. It's generally not equal to 0 because linear fit won't always be the best fit, and similar is the case for covariance. So it's almost always that linear regression would be biased because linear regression is not correct. So was it clear till here? Any doubts?
No.
Okay. So now what we are going on is estimating beta. Like it's what beta and you won't have all the values of xy as always. We'll just have observations, and then with again law of large numbers, we can say that uh, these converges to covariance of xy, and this converges to covariance matrix of x. We had an interesting discussion about this on channel. You can look it up previously. So basically, this linear fit, the slope of this line won't depend on the expectation of x. That's what I guess is trying to say. So what happens even if you just shift x to have a mean 0, it's just that this line will be shifted if you shift x to the left. So kind of the slope is independent of expectation of x. So you can assume that expectation of x is 0, and then you can still calculate what this slope of this line beta is. So if you go through that derivation, then this is what you get. The derivation as an v. This is how if you write v, and this is how if you write covariance of xy, you get this. So v inverse would be n times x transpose x inverse, and n and 1 by n cancels itself out, and this is what you get for optimal predictor. And how many of you have seen this equation? It was in N2NC's class again of machine learning. So you can also get the same equation if you just what I was saying earlier. If you just if you just differentiate with respect to x vector, this equation, and then equate it to differentiate it with respect to beta vector, and then equate it to 0. Then this is what you will get again. You just expand this out. And this is what the best fit, that is the slope of this line is. Now it may be that y is distributed according to this, that is y was sampled from this line, or it can be that y was sampled from an exponential distribution such as this. So we don't know that. Yeah. And then he's just making sure about the assumptions that I spoke, that you have not made any assumptions yet. No probabilistic assumption is needed to minimize the sample accuracy. And it doesn't say anything about how fast the beta will give you those results. Now what he's just seeing is what happens when, so this was the equation, and as I said, it is not generally true that this is equal to 0 or this is constant. But when is this true? So in linear regression, you'll always make such assumption that if epsilon comes from a standard Gaussian, then kind of this assumption is validated that the best model to fit Y is the linear model. So yeah, and why zero mean, as again it was said in the first chapter that even if it's not zero mean, you can kind of, this is like change of, you can shift the mean and then again it's still the slope doesn't change. So this is what the value of we got for beta. Y is x beta plus epsilon, and this beta hat is your predicted value, whereas this beta is the actual value. Like here you are assuming that this is slope is what fits the best value of y. So now it's just saying that it's just an unbiased estimate of that is this value is actually the best value that can fit y. So this is what it's saying. The expectation of e is equal to 0. So beta plus 0 goes down to beta. Again for same for variance that okay, this is also formula in multivariate case. You need to make sure that if it's A is a matrix, X is a vector, this will so this is just all similar to all the equations in linear case. These are sorry, in univariate case, these are the equations. In multivariate cases, so just again he has replaced y with beta hat with this value, and beta is a constant, so you can just remove it. Then again, what you are left with, this is what A is here, so you can just have this and A. This is what circle is written here. So here it should be variance of this. A is some constant. Now he's assuming that this, if this variance is actually, as I was saying, if we can validate this, if that assuming that it is actually independent, this if so if throwback, if actually it's not independent, then this variance would be some function of x. But if it's independent and we assume it to be sigma square I, remember that epsilon is also multivariate. It's a vector basically. So if it's just all of it, epsilon I is uncorrelated with epsilon j, and all of them share the same variance of sigma square. If this is the case, then this comes down to be sigma square. Variance comes down to be sigma square I. Yeah, this x transpose x will cancel. If this is just sigma square I, sigma square will just come out. X transpose x will cancel with this x transpose x, and you will be left with this. So sigma square x transpose x. So this is how your optimal slope predictor as its variance. So now here in this next section is telling about how changing different things affect your optimal predictor of beta. So first of all, beta depends on x as well. If you he has shown this diagram, this is a true regression line, the dotted one if you can see. Then whenever, say, if these blue samples are what X you have sampled, then the optimal fit would be this blue line. If the red is what you have actually sampled, red values, then this will be the new optimal line. So it's kind of the optimal predictor, or the slope of the optimal line would also be dependent always on what values of X you are what values of X you are taking it into consideration. Because obviously beta is dependent upon the V, and V is dependent on how X is distributed. Okay. And here he's just going into why this R square matrix is also not a good way to see how better linear fit is towards your data. Like R square is basically how much of the variance is accounted by your predictions divided by how much of the variance actually exists in the data. So if y is equals to ax plus epsilon, and we happen to know a exactly, so even if we have predicted a exactly, like it's the optimal predictor, the variance of y will be a square variance of x plus variance of epsilon. Here we are assuming epsilon is independent, uncorrelated with x. So, but our prediction would be just a of x. So what we are accounting from is only a square by a square times variance of x. So R square matrix is the numerator is how much variance our predictions have accounted, and denominator is what's the true variance, as we saw here. So this ratio is dependent upon variance of x. So it's not, it actually ideally should only be dependent upon A based on your predictions, but even on what values of X that exist in your data, the R square matrix will also depend upon that. So basically it depends upon your data. So it's not a good metric to how to judge upon it. Now we saw that beta depends upon x, where x is the data that you see. Here he's saying that beta also depends upon the values on variable z, where you won't even see what z actually is. So here he's making that case that here this is just law of iterated expectations, total expectations of path z earlier. So if given x, if y is independent of z, then you have no issues. But y can be dependent on x and z as well. So, but in your data, you have never accounted for z. So it's like, example, you have some data, the underlying, the data that you observed has not changed. But there are some factors that have changed y. So in that sense, your optimal predictor also changes. So that's what he's making a case here. He's taking x and z, y is just x plus z. So when only if you observe, if you takes x from normal distribution, and again z from the same standard normal, and y is x plus z. So what he's trying to say here is even if the marginal distributions of x and z are same, the joint distribution of x comma z will not just depend upon on the variances of x and z, but as I said, will also depend upon covariance of x z. That is how x and z relate to each other. So if we just change that you won't, just because you are observing x, you won't know that the covariance of x and z has changed. So there is no way to observe this change. So in the first case, it's just he has just changed it slightly from 0.1 to minus 0.1, and the optimal predictor completely changes. Because y is actually not dependent just on x, but it is also dependent on x plus z. If it was not dependent on z, then it would have been no problem, we said earlier. So because of this, the joint distribution of x and z changes, and that's why you also have to account for variables that you have never seen, and even that and these are the omitted variables, and even they can influence how what is your optimal predictor. Okay, any doubts still here? Am I going too fast or anything?
So like Fenil, so the last part that you said, Kamal, of like y is equal to x plus z. So in that it accounts for like kind of changes in both like the covariance between x and z, or like how is it? I'm confused between that part.
No, it depends upon x, it depends upon z, and it also depends on how x and z are related to each other.
Okay.
Here this variance of x and this is variance of z, but just because you are only observing x, so you have this, and even if the z doesn't change, but what he is just slightly changing here is how x and z are related to each other. So initially he took an example of 0.1 and then he took it as minus 0.1. Even this slight change in covariance completely changes your optimal predictor. And z is what are omitted variables that you have not accounted in your data.
Okay.
Wanted to know, am I going too fast? Should I slow it down or it's okay?
I think it's okay.
See, I mean, I think I'll again have to read back. I think the last few like topics were a little bit hazy for me. I'll have to like look back at it and then I'll come with doubts.
Yeah, even I think it would be better, like, because I didn't have the time to go through everything in detail for the second chapter. So,
What do you suggest? Should I go ahead? Should I explain it to you in more detail, the earlier sections? Or do you want to read the chapter first? I guess it's just better with me. So I guess I'll just complete it for the sake of it, then you can let me know. So here in errors and variables, what he's trying to say is there are, so first we covered that the optimal predictor depends on the distribution of x. Then we covered that the optimal predictor not just depends on the distribution of x, but it also depends on distribution of z, where z are the variables that you have never accounted in your data. Here he's saying that the x's that you have gathered also have some inherent noise. So what you might be interested is in u. So x is u plus this n is some noise, but you will never have u because the data that you have gathered will always have x. You can't separate u from n. So the example that he gives is when say you are asking for a salary of a person in a form. Now the person is not always going to give you the exact salary that he earns. It's not going to look it up and just estimate it. And now in that estimate also there is some noise. So you can't. So you might be interested in this exact salary, but that will never be available to you. So even this, even like the optimal predictor of y on x will be different than optimal predictor of y on. So even this extra noise can, because it's fundamentally changing what you're interested in, the optimal predictor also changes. But then further on he says that this is alright because in principle, even in your testing or even in the future, you are never going to be able to separate u and n. So because that you have, even though you are interested in y of u, what you have modeled is y on x, but since you can never separate u and n, the testing data and the future predictions you are always going to do on this model. So even in the future, you are going to get x. So that's never a problem. So there is error in variables, but for testing and prediction, that is not the problem. So that's it. Without better data, the relationship of y to u is just one of the unanswerable questions because you never have that data. this is an interesting part. So here is, it's like say y on x can be, y given x can come from this model log x plus. You can always write this in terms of this where epsilon is standard. These both are the same things. So if this is the case, then here what you can do is, there is no linear relationship between y and x, but you can transform x to log x, and there is a linear relationship of y with log x. But there is also other thing that you could have done is you could have transformed y to e to the power y, and would there be a linear relationship between e to the power y and x? So that's what he's trying to explain, that you always have two choices. You can either transform the response y or the predictor x, and what should you transform? So this might be also dependent on, as he says, subject knowledge, what problem you are trying to solve, and how y and x are related to each other. But if you don't have that, then it's always better to transform x rather than to transform y. So he gives multiple reasons for that. First of them, what you are actually interested in is expectation of y on x. I just type for such index expectation of y. But if you transform y, what you are going to get is expectation of f of y. And you can't just invert this function because these and this are mathematically not equal. So if you transform y, the prediction problem that you are solving itself changes, because you are solving for expectation of f of y, but you are actually interested in expectation of y. First is that reason. Second is you can, as in the case I said, it's beta 1 x1 plus beta 2 x2 and so on. If you are transforming x, you can transform x1 separately, as it has said. You can transform x1 to root x1, you can transform x2 to log x2. You can transform each xi separately if that is how y was your model. So you have multiple options in case of how do you want to transform x, but the same cannot be said about y, because if you go to transform y, it says there is no simple transformation that can that you have for y, but there is simple transformations for x and z that you can have. So that is second case, and in third case, what he's saying is here if you transform again y, what happens is, say as I said, it's best if epsilon comes from a Gaussian where the variance is independent of x, and say you have such a case. But now because you have transformed y, the epsilon will no longer come from a standard model. It will come from, he says, it will come from a weird nameless noise distribution where this has been transformed. Because if you have transformed y, the noise also gets transformed to some weirder distribution. But for the sake of mathematics, it's better that you have this assumption. And so, and once you have transformed xi to f of xi, then you can just solve it how you solve the linear regression, where you consider the f of x as the actual feature x1, and then you can just solve, you can just x transpose x inverse, you can just put those values in the optimal predictor of theta. In this equation. So your x transpose, the x vector would be after all the transformations that you have done. So he gives an example for that. So he just takes this example, y of x given log of x. So in one case he has transformed x to log of x, and in other case he has transformed y to e to the power y. So the results he gets are, so here this is how the actual curve is. Here he has transformed how x here he has transformed in this case how e to the power y, and here in this case he has transformed into log x. And when you when you switch it back to your case, then you can see that this green curve is correct prediction, and whereas the exponential of y doesn't give you the same result because the noise has been transformed into some weirder distribution. So, and you can have all the different choices of x. It's not necessary it should be some uh, just dependent upon that xi. F of y can also be a function of xi, xj, xk, whatever. F set fj to xi, xk, xi square, log of x, sin of x. Adding to the distribution. So now now here we are trying to make all of those assumptions, making it clear. We are writing it down which assumptions we are making and how sensible those assumptions are. So main assumption that I was talking about is this sigma square, that the errors, the residuals are independent of x. So basically y is equals to x plus epsilon, when u of x is your linear fit, and whatever else you see can never be explained with the help of x. So basically beta, the linear predictor, is the best fit to the y, because y given x would just be this, because epsilon is just independent of x. If this is our main assumption, and what sort of assumptions this equation has. As the thing, we are assuming that the regression function is exactly linear. That is, this is the case, and this comes from standard normal that is independent of x. The variance of the scatter is constant, indicates, if I just expand it out, in all the dimensions, this variance is always constant. And we are assuming that there is no dependence between this scatter and everything else. Again, all the covariances are zero. So they are not interdependent, they are not dependent on x, none of these are the assumptions that we are making in explicit right here. So now he's saying same thing, that these assumptions were not needed to derive the optimal linear predictor, but these assumptions are needed to say that the optimal linear predictor is the best fit for it. So if with these assumptions you calculate the maximum likelihood estimate of beta, don't think you would be familiar with maximum likelihood estimate. So it's kind of just in vague terms, it's like yeah, if you are interested, I'll write beta as W. So you are interested in finding this W. So with bias rule, you can write this down. This is a joint probability. So what you want is the bottom term would be independent of W. So you want to maximize this likelihood with respect to W. So what you want is to maximize this term. At the bottom there is, we just call it normalization constant, that is independent of W. So you want to maximize the numerator. So if you make this explicit assumption, y comes from standard normal, sigma square. So if this is what the probability of this is, sorry, y given x, if you just substitute it here and calculate the maximum likelihood, max given w, then what this essentially comes down to is your minimizing the mean square error. So you can look the proof of this online. So what you essentially do is you take the log of this. This is kind of like product of all the x's that you have seen. N is your number of data points. So if you just differentiate this, then what you will essentially be solving is mean square error. This simplifies to minimizing the mean square. So this is the maximum likelihood estimate of any function. So this comes in like Bayesian machine learning. So if you also factor in this P of W given X, then this is no longer a maximum likelihood estimate, but it's called maximum posteriority, MAP. Yep. Am I audible? Am I audible, right?
Yeah, you're audible.
Yeah. So if you also then assume this W comes from a standard normal, then if you also factor in this equation in this, then what you actually get is L2 regression. Not L2 regression, sorry. The term. But basic L2 normalization, I guess. No, not L2 normalization as well. What it was, L2 regularization. Sorry. So what you actually get is L2 regularization. But yep, you can look the proofs of this online. They are simple, and this is something that you should know. MLE and MVP estimates. So what he was trying to say previously is.
Unless your screen.
Your screen,
Yeah. Yeah, so what he was trying to say is that if you solve for maximum likelihood estimate of beta, so that's where all these assumptions come into picture. And the assumptions on epsilon noise. And so again, as I said earlier, this and this are the same things. You can write it however you write. U of x is x beta. Epsilon has sigma square I. It means equal. So this is where you will need these assumptions. And if you know that the maximum likelihood estimate of beta is same as the beta obtained by minimizing residual sum of squares, that is minimizing m mean square error, then you can say that, okay, the best fit for y is actually the linear model. So that's what you're saying. The maximum likelihood estimate is generically and certainly asymptotically efficient. That is, it's the best fit for y. That's saying. Then this part is just, I don't know why it's here. It's kind of just saying which parameters are important, and the more parameters you have, you'll always get better or the same model. You can never get a worse model with more parameters, because obviously there will be a more parameter space that you can have with more parameters. So yep, and now he's taking each assumption that we told and he's just breaking it down. And examining the residuals. The residuals, as I said, is just epsilon. Sigma square I. First is the errors have a Gaussian distribution. The errors have the same Gaussian distribution at each x. That is, they have the same variance. That is, all the diagonal entries are the same sigma square. And the errors are independent of each other. All non-off diagonal entries are zero. So these three assumptions that we have made about our residual, and then he checks that every time you make an assumption about this, you need to validate that whether all these assumptions do make sense or not. So rather than checking what is the model that you get or not, it is extremely important to see before saying that linear predictor is the best fit, that these three assumptions are always validated. So every time someone uses linear regression without these assumptions and does not test whether residuals are white noise and age of processes fits. Now the other thing that many people kind of get wrong into is say y is equals to beta 0 plus beta 1 x1 plus beta 2 x2. Say if beta 1 is 1000, after the optimal fit, you get beta 1 to be 1000 and beta 2 to be 0.1. What generally people try to make sense of this is that x2 has very less weight in predicting y. So x determines y, x1 determines y more than x2 does. Saying such kind of thing should also be warranted with many assumptions, and it's just making those assumptions. It's just telling when will it make sense to say things like this and when will it not. So whenever you test, so in statistics you make such tests that how much if you have beta 2, if you just remove beta 2, then how much of the right predictions you get for y, and if you have beta 2, then how much of the better you get. So after making those tests, so this is like a hypothesis testing that I think we studied in discrete mathematics. So first you have your null hypothesis. Null hypothesis is x2 doesn't matter, and then you have alternate hypothesis where you make the assumption that okay, x2 matters. So we assume that null hypothesis is always right, and then we see how much of the probability it makes sense. Like if it's 95% probability that x2 doesn't matter, then we say okay, then it's kind of like okay, x2 won't matter. So we establish that null hypothesis is right. But that's what he's saying, that our null hypothesis isn't that x2 doesn't matter. It's like x2 doesn't matter with all of these conditions. So it's like the alternate hypothesis is not just beta p is not equal to 0, but this means even beta p is 0 is equal to like x2 doesn't matter. Right? But beta p is not equal to 0 in a linear Gaussian noise model, which all includes all the other variables. So it's kind of like your hypothesis is this and not just that x2 doesn't matter or beta p is xp doesn't matter or beta p is not equal to 0. So that's what he's saying. This beta 2 is not just dependent upon x2, but beta 2 is also dependent upon x1 and all the other x3, all the other xi's. So since the value, even though value of beta 2 is less, it doesn't equate that x2 has less contribution, because again x2 determines the value of all the beta i's, and all the x's determine the value of beta 2. So that's what he's mainly saying here. And yep, basically that's what I covered. And then here I think you can just read all of this. It's just making, it's all like just there's no mathematics involved. It's all easy. You can just read it, and when to use linear regression and when not to use linear regression is not the best tool that you have. All of these things. So this is fairly easy. So I guess we are done here. Any doubts? Guys?
Not currently, but like we'll go through material once, and like maybe if we can next session we can ask doubts regarding this.
Sure. You can just send them on Slack or wherever you.
Yeah,
Yeah. So yeah, that's it from mine. So how do you want to? How do you see the timeline? That how do you want the chapter 3, 4, 5 discussion? Should we will read them and just send us your doubts, or should we take another session?
this is my suggestion. I think we can have kind of like tomorrow as a break, kind of where we revise and like also go through the material for chapter 3, and we can have like a meeting on Wednesday, like alternate days, kind of like that, maybe.
No. Let's just have one meeting now for all 3 chapters.
Okay.
These 3 chapters aren't that big, so it's
Yep.
better if you go through all 3 chapters once and then we'll have a single meeting rather than organizing a meeting every alternate days.
Yeah. So
Okay.
if you are just walk down the chapter 1 to 3, 4, 5 are fairly easy as compared to 1 and 2. So that's
Yeah,
why we
three
broke
and
it down. Yeah, 3 and
three
5
and
are
four
much
are
easy.
pretty. 4 is a little complicated, but if you read it once, you'll get it. I think for 4 there are a lot of notes on the channel as well. So if you have some doubts in the derivations, if you go through the notes on the channel, you'll find an answer for that.
Okay.
And Swapnil has a recording for chapter 3 also, so you can go through that recording.
Yeah. Yeah, Ananya was saying something like I just.
Yeah, I was just saying, can we have it like the next session after we've read it next week, or I think all of your exams next week, right?
Yeah.
Yeah. So we could do a session on maybe Saturday if you guys want. Saturday or Monday, whichever day is
Monday,
comfortable for you guys.
Monday night works for me. Not Saturday. I have my exam on Monday, so
Okay, yeah.
like Monday morning I have. So
Okay, yeah. So Monday night works for us as well. Like I don't know, we'll decide, but I think anytime next week will be okay. Like
Yeah, it,
we
it,
have our
it
exams, but
depends. Yeah, it depends on how you finish it. Like, suppose some of you, I guess, even some of chapter reading 1 and 2 is left. So I guess you read. So once you start reading, you will get an idea of how much time it will take for you all, and then let us know when to schedule the meeting. Yeah, but first,
also how do we go about while we're reading? So like this time what I did, I because I remembered everything fresh from yesterday, I was able to recall a lot of stuff, and then if I didn't get, I just searched online, and I think there's some link on where for each chapter. But how do we go about further? Like if you have to like read the chapter 3, 4, 5, like making notes and stuff. Even during these lectures, we make notes. Do we just listen? I'm not sure.
I think making notes would be helpful, but I haven't yet. So
yeah, neither have I. I usually just I just note down something in the PDF itself. If I have a
Okay.
doubt, if I think something is important, I highlight it in the PDF itself. So I mean that generally works for me. But if you find that taking notes is useful for you, you can do that.
Right.
As for the there are often terms which are this book is actually not meant for us. There are supposed to be a lot of courses which are done before you finish this book. So actually, the author expects that we have taken 2 or 3 statistics classes before we actually start with this book. But so there are a lot of things which are unexplained. We just mention it, and
Right.
so what we do is we have to go and search for it. He tries to explain it as much as possible, but sometimes he just mentions that okay, this is we have already covered this in a previous class or something. So what you have to do is for that particular topic you have to go and read up on Wikipedia or something.
Right.
yep. So for this, like while reading this chapter's TALR book, we found it to be quite helpful. Me as well as Parth. So I guess this TALR is just an entire book on chapter 2. So it's kind of like that. So I guess there is the link for Truth About Linear Regression, so you can refer to it when, like, not entire thing would be helpful, but most of the linear regression paths that you can't understand would be there in TLR.
Yeah, I look into that.
And apart from that, like what I gave you on yesterday was just a very small intro on statistics. But if you want to like look into it further, then there is a good fundamental course of stats on YouTube. It's Harvard Stats 1110. It's taught by Professor Blindstein, and it's quite good, and it's very fundamental. Like you would know most of the stuff from it, but just go through the lectures, like go through the topics that you don't recollect or stuff.
Okay.
And then there is also there is this for linear algebra. This three blue one brown has made a very good playlist of getting intuitive understanding of what uh, ranks and what actually the linear algebra, how does it make sense, what exactly is intuitive way of understanding determinants and ranks and stuff, eigenvalues and stuff like that. So it's I guess 12 to 15 videos playlist. You can also go through that. It would be a good fresher and good way to intuitively understand concepts and this.
What was the name? Can you repeat?
Three blue, one brown. There is this playlist on linear algebra. You just go
Yeah,
to
Grant Anderson, right?
yeah, grandson. And even he has made one. I guess Kushal also sent a link earlier yesterday of contour plots. So he has also made a series on Khan Academy about differential calculus. So if you if you want to know about I don't think differential calculus helps much in this book, but it's kind of a necessary thing when you want to derive things for matrices and stuff like that. So there is this Khan Academy's playlist on differential calculus is also quite good. That is taught by Grant Sanderson.
Okay. And like for this particular like book, like is linear algebra like needed to be studied in detail, kind of like from, or it's like kind of from the, let's say, like eigenvalues and all like that particular only like.
It depends on what level you want to understand it. So sometimes there are statements that if you don't entirely understand it and just skip it, then there won't be much difference. You can understand the chapter in its entirety. But if you just want to get like drill down on what exactly he meant by one sentence, then I guess it helps knowing about linear algebra and differential calculus and stuff like that. But yeah, even though if you don't do that, then I guess it's quite alright and you can navigate it through. And for if you that the linear algebra stuff for the three blue one brown is just like a very small things on like just intuitive understanding of stuff. But like if you actually want to know, yesterday I also talked about positive semi-definite matrices and stuff like that. So if you want to know things like proper course that you want to do, then there is again one brilliant course of MIT on linear algebra that is also available on YouTube.
Yeah, Gilbert Strand.
Yeah, yeah. So that is also very quite renowned. So you can also refer to them. Refer to that.
Okay.
Okay. Anything else?
Okay, so I guess we are done for the day. Once you guys read all three chapters, you can let us know. So then we'll try and arrange a meeting next week.
Okay. So like you won't be like going currently like for this week, no? Like you will be starting from chapter 6 after like your exams and all that.
We don't
Probably
know, but
yes, but yeah, we are not sure. It depends also on the
Okay.
timings and depends of when schedules the meeting.
Okay.
okay, good. Bye. Good night.
Bye.
All
Bye.
right.
I thank you.
Bye.
Bye bye.
Thank you.